Good afternoon to you all. I'm Kapil Oberai. Welcome to the session on overview of big data analytics, and I'm a faculty at the Geoinformatics department at IIRS. So in this session, we'll try to cover what we mean by big data and how we can define it, followed by what we mean by big data analytics and its type, and how does this geospatial data relate to this big data concept and what are the challenges. Finally, we'll also see what are the various frameworks that we can use for this big data analytics. Primarily, there are two major frameworks. One is Hadoop and second is Spark. And then we'll also talk about the cloud computing and how does it helps in analyzing the big data. Coming to the term big data, first let's try to understand what we mean by the term data. So data, as we know, is called as the raw facts. And once you process the data, it becomes an information. Now, the data are the seeds based on which we make our decisions. And in the today's modern world, the decisions are primarily data driven. Hence, we say that the ability to make data driven decisions is very crucial for any business or any organizations. So data are basically the underlying sets over which we could make our informed decisions. Now coming to the term big data, the moment we use the word big, the first thing that comes to the mind is talking about size or let's say the largeness. However, we also know that size is primarily relative, because a big for one person may not be a big for another person, like a big house or a big car. And also with reference to the data, we generally say that data is already evolving. A lot of data is being generated, captured over the years. So size may tells about the volume, but is it the only parameter? And in the subsequent slide, we'll try to answer some of these considerations. Now to understand big data, let's see the definitions. So definition reads like this. It says big data is defined as huge collections of myriad or various data sets which is difficult to process by using traditional data processing platforms or current state-of-the-art approaches for data processing. So the thing it is highlighting is data that is huge collection, obviously talking about size, and also myriad of various kinds. The second definitions, which basically extend the first one, more emphasis is given here like that it is a term for collection of data sets, again talking about large and complex. So the idea is something that is data sets that is of large collections and also of the complex nature. We could also think that something we can't put into a laptop or a single desktop based memory system, and something which will be very difficult to process using the traditional, let's say, database management tools or traditional data processing based applications. So the big data definition primarily highlights the talking about the vastness or the largeness and also the complex nature. Now the one important question that will be there in your mind is, when we are talking about big data, is the data, as I said, is already evolving. Why does this term we are using nowadays, and why this is taking a front seat? Now to understand this, we need to kindly keep in mind how does the data has evolved, what are the impetus that leads to the huge collections of data. That could be more from a commercial perspective, and also in our geospatial sector there are more number of satellites, different types of satellites are all contributing to the big data bandwagon. Now to understand the data deluge kind of a thing that we want to emphasize here is, this is an infographic which talks about the data that is generated every minute of the day. This is given by a company, US based company called Domo. As you can see from this figure, the caption reads like data never sleep, which is perfectly true statement. And here you can see that it talks about some numbers which talks about the data that is generated at every minute of the day. Remember, we are talking about every minute. For example, how many people are doing searches? It is like 5.9 million Google searches. Similarly, around 3 billions are doing the 3 millions are doing the YouTube video views. Similarly, Facebook, and roughly around 251 million emails are sent. Now, the this as the data is being generated, obviously the thing is there are more number of people who are users of these kinds of platforms. So apart from web being a consumer of information, in a web 2.0, it's more like the user also contributing the data sets and the services. Another thing that has led to the huge amount of data is that the internet penetration has also increased, as you can see from the this figure here. In 2014, around 3 billion people were having access, but now it is 5.5 billion. And also, if we see perspective, the internet availability has increased. The smartphones are also being used as a sensors for data collections, data manipulations, and so on. All leads to the huge amount of data being generated. These are mostly the web-based companies who are providing services to the users. But the same will, as I mentioned, will be also be applicable for our geospatial sector, where also the data is being generated through various sensors and instruments on board. That could be satellite or could be aerial, could also be the ground-based sensors, and along with other attributes information. So in the data deluge era, we are talking about that there is a huge amount of data being generated. However, as this infographic mentioned, that data is the new oil, and just like we need to refine the oil to make use of it, similarly the data has to be refined to make value added decisions. Hence we say that the ability to make data driven decisions is crucial for any business. In the case of web based companies, it's like providing the recommendation for the next type of videos, providing value added services. The next time you visit Netflix, it will give you some recommendation of the people who have watched similar kinds of movies, and based on that they want to increase the user experience and also serve them in a better way. So hence they are making use of this such huge amount of data to make a data driven decisions, in this case to help their customer base and also to provide them a value added services. Now talking about the numbers, so if you remember in the school days we used to learn about the bit, which stand for 0 and 1. Nibble was 4 bits, byte was 8 bits, and kilobyte was 1024 bytes. Now all the way nowadays we are talking more in terms of gigabytes and terabytes. And as you can see from this table here, that the terabytes is around 10 to the power 12, and then petabytes is 10 to the power 15, and the zettabytes is 10 raised to the power 21. So you can see the number or amount of data that is being generated. One of the figures talks about that the annual size of global data sphere will reach around 175 zettabytes in 2025, and so these are from the basically from the sheer volume of data that is being generated. And same is true for our geospatial industries, where also the data is the backbone for making informed decisions. Now talking about the volume perspective, which is the size that a lot of data is being generated and captured, and also the impetus regarding the availability of the sensors or availability in the previous cases of web-based companies will be the internet and penetration and the smartphones and so on and so forth. The other things that also led to the complexity of such data is that the most of the data that we are generating comes somehow fits into the semi-structured or the unstructured in nature. So let's try to also see what we mean by structured, semi-structured, and unstructured. Structured is something we are used to, and we somehow find it convenient to handle and process. So the moment we say structured data, we are talking about data that have some kind of a organization structure. In the pure database perspective, we can say a kind of a database schema, which talks about the structure, the data being organized in forms of rows and columns, and that is a simple way for organizing our data, where we know that all the data sets will follow a similar structure, and we will somehow try to put our data into those buckets or as defined by our schema. Another example of the structured data could be our Microsoft Excel or a comma separated values files, where each record will denote certain data points that we want to capture, all confined to a particular structure, where the first will denote first attribute, second attribute, third attributes, depending on the type of business problem and the type of data that we are capturing. Now, completely opposite of this structured data is something we call as unstructured data. As the name suggests, it means that the data does not confined to any predefined organizational schema. And good example of this is, let's say, the media post from the social media. For example, if I talked about the X platform or the Twitter platform, and also the messages from other social media based platforms. Now it's very difficult to put them under the different, or very difficult to define them within a particular schema, because most of the things will not, for example, messages that some one person will post will not follow the same structure as the another person. Because in a social media based post, you could put text, you can put emojis, you can put a table, you can put an image, and you can put in whichever order you want. And hence it does not confine into a particular structure. And taking these kinds of data and trying to put them into buckets or a schema definition is very, very difficult, as I said, because all media posts don't follow any kind of a structure. In fact, these kind of platform encourage users to put their opinions, views onto such platforms, and such platforms are also being found useful in various domains, like knowing about the product, the services, where people comment about their experiences and their experience on using various kind of services or platforms. So we talked about the structured data, which means data that follows a particular structure. Examples may be a Microsoft Excel or CSV file, or from database perspective is something we define as a schema, and then try to each data we want to insert will follow that particular schema. Unstructured, which means the data does not confine to any predefined schema, and then good examples are the information that we collect from the social media platforms, like posts from Twitter and so on. Now, in between, we also have something called as a semi-structured data. As the name suggests, semi-structured means the data that has both the elements. So some parts are can follow a particular schema perspective, whereas some parts are purely arbitrary. The good example of this is something we call as a email message. Now, if we look at from the emailing system perspective, you'll see that some part is structured, which means to field, from field, subjects are some kind of fields which all the email messages will have. However, the body part which we try to communicate with the other person is completely arbitrary. Again, it does not follow any structure, which means somebody can put a table, somebody can put a bullet point, somebody can put an image, and so on and so forth. Now, one of the good example of this semi-structured data format is called as a JSON, or the JavaScript object notation, which primarily use the key value pairs to denote and represent such kind of data sets. As you can see on the right hand side is an example of a JSON based data being represented in JSON format. As you can see that it uses a JavaScript based notations where we have the key and the value pair. For example, ID, some number, first name is Jane, last name is Wu, and similarly we have an address, and then the hobbies may be surfing and coding. So again, here it use all the different kinds of elements that we want to code the information. For one person there could be one hobby, for other person could be multiple hobbies. Similarly, somebody may be having a particular street name or a city. In some cases, some of the information may be missing. So basically, it allows us to comprehend and store the information in a key value pairs, wherein it has both the schema perspective and also some part which could be arbitrary. So just to summarize that, structured data, primarily we talk about data sets that confine to a predefined schema. That's like CSV or Excel file, or the database concept of schema. Semi-structured, something we call as a JSON object or an XML object. And similarly, from the unstructured data perspective, it is like storing video, audios, documents, and so on. And as I mentioned, most of the data sets that are being generated are more falling under the category of either unstructured or the semi-structured. Now, having talked about the definition for big data, talking about large and complex, now one of the other good way of representing or defining something called a big data is represented by the characteristics or dimension denoted by words starting with the letter V, known as the dimensions to big data. Initially, it started in 2001 with Doug Lane giving 3 V's, talking about the dimensions like volume, velocity, and variety. Subsequently, the other V like veracity was also added, and the IBM also added the term value. So now 5V is like a agreed upon characteristics to define the big data. So one of the good way of defining the big data and how it's different from the traditional data sets is to consider these V's or dimension of big data, talking about the volume, velocity, variety, veracity, and the value. The moment we talk about volume, we are talking about the amount of data that is being generated. So this talks about the size perspective. However, size is not the only consideration to make it more like a complex based data sets. What adds the complexity is the other we call as the velocity, which talks about the speed of which the data is being generated and needs to be processed. For example, we could have a batch based system or a stream based system. Batch means it is like a payroll system where at the end of the month we need to compute the salary. Or it is like a continuous feed of social media data that is coming that we need to process. So there is a complexity in terms of one-time processing to the continuous based data analysis that we need to do. The third V is called as the variety, which talks about the type of data, as we mentioned, structured, semi-structured, and the unstructured. So as you can see here, volume is only one aspect which we're defining from the big data characteristics, which is the size. However, the other adds more complexity in terms of the speed at which the data is being generated that needs to be processed, the various kinds of data sets. Again, as I mentioned, structured data is something we are used to, and we know how to handle it with the traditional technologies like the relation-based database systems. But how we could handle this semi-structured and unstructured data, because it's very difficult to somehow put this or try to convert from semi-structured or unstructured into the structured format. So that's add more complexity. And another way of looking at the variety is the moment you have multiple or diverse kinds of data, the integration also becomes a lot of challenge, because we need to agree on the standardization of the formats, the standardization of the fields, and other aspects are also to be considered. Now, veracity is also very important, which talks about the trustworthiness or the authenticity of the data, and becomes very, very important when we talk about, let's say, the social media data that we are used to handling. Now, social media data is the data sets being contributed by the users. Now, they also provide a facility wherein they can also, let's say, geo-encode the information that they want to submit. So, the like Flickr or Instagram, it is also possible to put or post the geocoded images, or in the case of Twitter or X, we could put the geocoded tweets. However, the trustworthiness from the perspective of the data being generated, also let's say from the geocoding perspective, whether the location accuracy and etc. thing has to be considered. But ultimately aim for this of capturing this whole data and making a value-added decision is called as the value, which talks about the business value of the collected data, how we can use this data and then processes to use it for making some informed decision. This is the whole idea. The value primarily highlights the analytical parts from the big data analytical perspective, saying given this vast amount of data of different speed of generation, different types, the veracity perspective, how we can generate the business value and use it for our for making some informed decisions. And then if you look at this this infographic again, there is a challenge in handling the big data both from the acquisition perspective, the storage perspective, also how should we search it, analyze it, and how do we visualize it. So it puts a whole challenges in all the aspects from acquisition to the rendering of the data sets. Another way to look at this infographic is that these are not independent also, volume, velocity, and variety. For example, if we increase the velocity, let's say the speed of data being generated, the volume will increase. Similarly, if the variety, the data types increase in a project, you are consuming data from various sources, then obviously it will leads to the volume increase in the volume. So we could not only see them from the individual perspective, but these are also interdependent among the others. Now, having talked about the big data and the characteristics of qualifying something as a big data based on those 5 V's, now let's talk about what we mean by big data analytics. Now, big data analytics involves examining large and myriad types of data, which include structured, semi-structured, and unstructured, and the aim is to uncover or find out the patterns and insights from the data sets. So the big data analytics primarily works on the big data, considering the various dimensions, the different types, and the aim is, can we identify certain patterns and insights. Now we could also categorize big data analytic into various types, as I'm showing on the left hand side here. First is called as the text analytics, where we are processing of or extracting the information by analyzing the unstructured text data. This is like extracting the information from blog post or survey responses. So text analytics primarily aims at identifying the patterns or retrieving information from the unstructured text data. The second type of a big data analytic type is called as the audio analytics. As the name suggests, it refers to analyzing and also extracting information from the audio data sets, and these kinds of applications you will find in the customer call centers and healthcare companies, where they want to record and understand the customer experience, the call center official how he is communicating with the other person over the phone, and so on. The third type is called as the video analytics, wherein it involves analyzing and extracting information from the video streams. Now these kinds of applications you will find under the video surveillance kinds of applications in commercial or organization perspective. The fourth type that we have is called as the social media analytics. You could also think as a subset of text-based analytics, but this is being made as a separate category because of the popularity of these platforms and usage of these platforms in various kinds of domains. So if you happen to look at the literature, you will come across the social media data being used from the geospatial perspective in the case of disaster like flood, earthquake, and so on, where the user could contribute by informing the government officials or the authorities about the damage onto the ground and other perspective. So social media analytics involve analyzing the data from the social media platforms, which could be Facebook, Twitter, etc. So they also bring their own set of complexity about retrieving data, analyzing data, and finally making sense or getting the information that we desired. The other type is called as the predictive analytics, which involve predicting the future outcomes based on the past and the current data. Here we can use of various statistical and machine learning techniques for making that future predictions. Now if we try to put a process flow about how to go about and doing the big data analytics, is we could think in terms of two phases. One is a data management phase and second is the analytical phase. So in the data management, we involve the steps like acquiring and recording of the data sets. Obviously the data sets has to be extracted, cleaned, maybe integrated, and before putting to use. So these are the stages through which we go about in the data management, followed by the analytics, where we are using the various modeling and analysis techniques, and finally visualization or interpretation based ways for communicating the results that we get to the end users. So big data processes will primarily have two phases. One is data acquisition and storage management perspective, and second is the analytical perspective. Now coming to the from the big data generic perspective, how does this big data relate to our geospatial data and what is the importance? Now, as I mentioned earlier, geospatial data, if we consider the big data characteristics that we define, will fit into those V's that we have talked about. However, geospatial big data, if we could define it, will mean to refer to massive data sets with spatial or geographical components. Again, the data is collected from diverse sources, and in the subsequent slide we'll talk about what are the various sources of geospatial big data. But we do know that these geospatial data sets are very important for any societal or governance applications, and we have seen them being used in various diverse applications and user-based applications. So earlier we used to have the Millennium Project, which identified 15 global challenges, as you can see here on the right hand side. One in the boxes denote the let's say the challenges in which the geospatial data will have a huge role to play. Now this Millennium Project has been replaced with the Sustainable Development Goals, which are 17 in numbers, and in those Sustainable Development Goals, geospatial data plays a very important role in trying to address those kind of goals achievements. Now let's also talk about what are the various sources that to the geospatial big data. One is pretty much obvious, which is the Earth observation or the remote sensing data. Now one of the way to look at this data sets is that there are various space-based agencies who have their own satellites through which they capture data. Now this infographic just talks about few of the sensors: Landsat 7 and 8, MODIS, and Sentinel 1, 2 and 3 series, and it talks about how over the period of years from 2013 till 2019, how much the data is being generated. So in 2019 we are reaching around 4 petabytes. Now petabytes is 10 raised to power 15. However, as I mentioned, this data is continues to evolve and these are only few of the sensors that we used, and also from few of the agencies which are having their satellites. So if we can go to the next infographic, which talks about the various countries and number of satellites by nation, and you can see from this there are other countries who are also having those satellite based systems through which they are capturing the various information about the Earth physical and biological processes. Now India roughly have around 55 satellites, out of which 21 are of the Earth observation in nature, and there are various other kinds of satellites like communication, space science and navigations and others. However, this Earth observation data is being continues to increase. Now this is only the, let's say, the satellite based platforms, but there could be other aerial based platform, UAV, all contributing to the vastness or the large amount of data that we capture. Now another way of looking at the Earth observation data will be that there are of diverse kinds. So we have a hyperspectral, multispectral, panchromatic, again of various kinds of data formats collected through various kinds of platforms. So all are coming under this the sources of geospatial big data. The other type is that we should not forget is the surveying and mapping data that is being collected past as well as the present, which is also being the data we will required in our various projects to do some analysis. The third type is called as the location based data. Now this is more like a mobility based data or GPS based trajectory data that is also being used either for fleet management or optimizing the location or navigation perspective. The fourth type is the social network data. As I mentioned, most of the social media platform do provide users to post their views and opinions, which could also be geotagged and then also be making use in various scenarios, could be disaster or opinion mining and other aspects. Nowadays there are also a lot of IoT devices or Internet of Things devices which are also being generating the different types of data which being corrected at high velocity. For example, temperature, measuring the temperature, air quality, pressure, and so on, soil moisture, etc. Now, if you look at these categories or the sources, you will see that all are of different types and are having the different data formats and may be required in a typical project. So, how to handle and some make sense of such data is always a challenge. Hence, we mentioned that acquisition, storage, manipulation, analysis, and visualization is a challenge when we talk about the diverse sources. Now, so having talked about what we mean by big data, how we can define it, the characteristics, the types of data like structured, semi-structured, and unstructured. Also talking about how does the big data relates to our geospatial, and also having a understanding of the various sources of the geospatial big data. Now let's also talk about what are the various analytical frameworks that are available to handle and analyze such data sets. Now, one thing we will be sure about is that working on a standalone system, or let's say laptop like a system, will not be a way to go. What will required is a kind of a cluster computer, which means a group of computers working together to solve that large data problem. Because these kinds of diverse and high volume data sets will not be able to fit into a one single machine. So hence we require the power of multiple computers which are working together to solve certain these kinds of problems. Now, two of the very important frameworks that under the big data category is called as the Hadoop based system and the Spark based frameworks. First, let's talk about the Hadoop framework. Now, Hadoop is a software framework. It is an open source which enables the storing and processing of big data on the clusters computer. Now, there are two parts or two components to this Hadoop based framework. One is the underlying file system, which we call as the HDFS, which stands for Hadoop Distributed File System. HDFS, Hadoop Distributed File System, which provides the underlying storage capability with fault tolerance and redundancy to store such data sets. Now, it is a distributed file system, which means it divides the large files into small chunks, and those chunks are being stored across many machines for seamless data access. The good thing about such a distributed file system is it can store both structured and the unstructured heterogeneous data. Now, why there is a need for having this distributed file system with redundancy and fault tolerance is because we want to maintain the availability of such cluster environment, because if one of the node goes down, then the process will be halted. So we want to build this redundancy and the fault tolerance into the underlying file system. So to look at this infographic on the below, where we have a file which is divided into three parts, or block A, block B, block C. Now, suppose there are 4 nodes, D1, D2, D3, and D4. So as you can see here, the different blocks are being stored in replication in various nodes like D1, D2, D3, and D4. So in case if the D1 is not available or goes down, still the data could be fetched from D2, either D2 node or D3 or the D4, which means it support. So still if the node fails, the process can continue because the data is available in a replication manner in other nodes also. Now, the second thing we should also note is that most of these data sets that we talk about, especially the geospatial data sets, are of very large size, GBs or terabytes. And most of the time goes into this input output operation, which means fetching the data from the disk, bringing into the memory. So these kinds of distributed file systems take care of the replication, also maintain the data locality within the nodes, so we could avoid the IO cost and spend more or where the node can process the data that is locally stored onto those systems. So one of the component is the file system, a distributed file system called as the HDFS. The second, to support the data analytics, there is a framework called as the map reduce, and we'll see in the next slide what we mean by map and the reduce. Now, map reduce is a programming paradigm. Think it like this as an analogy, like given a large task, we could break it into smaller tasks. That portion of the task will be executed by n number of nodes. The answer of those tasks could be accumulated, and finally push it back to the another operation called as a reducer, which combine the result of those intermediate operations to get the final result. It is like chunking the task. Each portion of the task given to one machine with the data that is available on that node will be processed, and finally the individual small task will be combined to get the final result. It is like a scatter and a gather, or a divide and a conquer kind of a method. So there are two phases in this map reduce framework. One is called as the map phase. In the map phase, what we do is we divide the large data sets into smaller pieces, and we dispatch those small pieces onto the nodes into the cluster. Now, one more thing that we should also be noting in such kind of a distributed environment is, one thing I mentioned about data locality. Other thing is that we are trying to push the application to the data, or not the data to the applications. So the aim is that the application should run locally where the data is residing, so that we can cut down the input output kind of an cost. Now the second phase of this map reduce paradigm is called as a reduce phase, which primarily collects the result from the map phase and process them to get the final result. So the idea is, given the large problem, break it into smaller equal size parts. Let's say give each node one particular portion of that task which works on the data. Similarly, other nodes can work on the same data sets onto their local nodes. The different second phase is a reducer, which could collect data from such nodes, and finally all the results could be collated to get the final result. Now, to understand this, let's see one example. Let's say we have a DEM data sets which is we want to process. Suppose it is of we are looking for processing this data which is of let's say large geographical coverage, then we want to process it. So the idea is, can we split these data sets in terms of tiles? We could define a tile size, and then we can break it down into those tiles. The individual tiles can be given to the different one individual nodes, wherein those tiles are being processed. Finally, the results of those intermediate tiles processed by those mappers could be collected by a reducer operations, which in turn store the result back to the HDFS system, which could be utilized for further processing. So here what we are trying to do is taking a task, in this case process of a DEM, break it into some smaller portions like tiles. Individual process on those DEM will happen on those map individual nodes, and then the reducer can combine it. So primarily in this MapReduce paradigm, what we need to provide is two program. One is a map program which somehow divides the larger task into smaller tasks, and a reducer which can collect those intermediate outputs to combine it to get the final output. However, this MapReduce or this Hadoop framework is good for a batch kind of task, not for a, let's say, the stream kind of process. The reason being is, if you look at this graphic again, the mapper reads from the disk, write to the disk, again reducer again read from the disk and write to the disk. So there's a lot of reading writing that is happening, which slows down the process. So there is another framework called as the Spark based system, which primarily provides in-memory computing capabilities to process such large data sets. So they, compared to Hadoop, they provide much more performance improvement by eliminating the need for reading and writing to the disk. As I mentioned earlier also, this reading and writing is a slow operation. Input output is a very slow operation compared to a computing or a CPU bound operation. The Spark makes use of the structured college and resilient distributed data sets or a data frame from the Spark 2.0 version onwards, and this whole data sets is stored in kind of an in-memory storage. So hence the reading and performance is much faster. So Spark is much faster compared to the Hadoop based system. Now the other way of looking at this Spark based solution is that it provides a whole gamut of libraries or tools for us to use. So apart from the Spark core, which is the basic building block to support this in-memory computing, it supports Spark SQL for structured data processing, Spark streaming for stream-based application, MLib for machine learning kind of application, and GraphX for graphic or let's say the network-based studies. Apart from that, it also supports multiple programming languages. So here we can use Python and R, whereas in the case of Hadoop we are primarily restricted to the Java-based platforms. Just a moment. Yeah, so compared to the Hadoop based system, Spark is provide much more advantages compared to the as I mentioned, the Hadoop based system, from the types of support that is given, along with the support for various kinds of libraries or the tools that you could make use of. So think of in terms of Spark as a unified processing framework through which you can do various kinds of tasks, whereas in the case of Hadoop you need to install or use different libraries to support that particular use case. Now the other types of big data analytical system that are come up is called as a NoSQL system. Now NoSQL means not only SQL, and the terms primarily denotes the database systems which departs from the classic relational based system where we stored data in the forms of tables, as you can see here, in the forms of rows and columns, which is primarily restricted to the structured kind of data with the schema enforcement, whereas NoSQL provides us the leverage to use other kinds of data formats, let's say either to organize in forms of a documents, key value pair, columnar based storage, or a graph based storage. Now these are from the ground up made to support scalable application with high performance in mind. And also they are obviously distributed in nature. Now comparing, if I just maybe if you see this infographic here in the below, which talks about scale up versus scale out kind of a system. So traditionally in our relation databases we predominantly install them on a one machine. As the load increases, we try to add more RAM, more CPU, or more storage to cater to that needs. But there is a limit of how much vertical scaling we could do. However, NoSQL system are support horizontal scaling, or we call it a scale out, which means they allow multiple nodes, or in this case community hardware, to be added to the system. So as in when the requirement comes, a new node could be added to support the, let's say, the increased load, and when the load comes down, the node could be taken away with. So hence vertical scaling versus this horizontal scaling, apart from the advantage of not schema enforcement, support for scalability, various other kinds of storage format that we can use. Now in the big data perspective, we also have various spatial based derivatives of such Spark and Hadoop based platforms. So one example is a spatial Hadoop, which allows us to store and analyze our spatial data sets, primarily vector in this case, and supporting the various vector data types, along with the spatial operations can be done. Another is called as a GeoTrellis. Now this is more of a Spark based platform which works on the raster data set. So looking for, let's say, high performance application with reference to processing of the raster data sets, this Spark based solution could be one of the options. Now there are others also. For example, this Apache Sedona is also one of the solution to, again, from the Spark based frameworks. It is an open source which allows us to store and process large geospatial data. Good thing is it can handle both raster and the vector data sets. And other advantages, maybe it provides you that SQL kind of a syntax, which means those who are not well versed with, let's say, programming languages, maybe can use this SQL kind of syntax for performing large data processing, could be handling both raster and the vector data sets, and it can work on a distributed environment also. So we talked about few of those solutions. Now there are other kinds of data management solution with reference to big data. One more is called as the RAS daemon, or the raster data manager. Now this allows us to store our raster data sets more natively, because we know that our raster can be treated like a array or a matrix, where the individual bands could be, think in terms of like a multi-dimension array of a certain rows and columns, and bands could be the depth of those number of bands, and it allows us to store these raster data sets along with the querying capabilities. Now good thing about such platform like raster data manager is it also supports our OGC based standard. So it complies with the OGC based standard of web coverage processing, which is primarily used for handling the coverage or the raster data sets, along with support for the, let's say, the ad hoc based queries called as the web coverage processing service, wherein we could write, again, not a programming language code, but a, let's say, a query based interface for either fetching the data from the system and then using it for various purposes. Now think in terms of that the data is organized in the form of this let's say a cube, and then we could extract either one band, we could slice and dice and retrieve the information that we are looking for. For example, if given an image, we just want to subset only 500 rows and 500 columns from an image, we could just write this simple statement and we'll get that. Similarly, to compute the NDVI, we could use this, again, a query based interface to perform such task and render it back to the user. So how we can make use of it? You can use it as a backend raster storage solution, and then use it and use the various web-based interface or any graphical user interface to fire the query. The data will be processed onto this server-side location, which could be simple band-based operation, or it could be as complex as let's say, some multi-criteria based analysis, or maybe an AHP like a technique. and the output can be rendered back to the user. So all of the data processing is handled here, and user can be just given the outputs in the form of images which could be rendered onto the users. Now since it is always already compliance with our OGC standards, so from the geospatial perspective it becomes much easier to integrate our web-based or desktop application with this with minimum of effort. Now this is one example or case study that we did as a part of the MTech project, where we try to compare some of the SQL on Hadoop based frameworks. So SQL Hadoop primarily refers to those analytical system that allows to query data stored onto the HDFS using the SQL, which is a declarative query language called as a structured query language. So in this study, what we tried to do was try to compare various SQL and Hadoop based frameworks, like Hive on Tez, Spark, SQL, and also the Presto, and then we compare it by varying the data size from 1 million to 200, let's say, million points, let's say, also the varying sizes, and comparing them with various kinds of queries. As you can see, queries could be of circle type, bounding box type, or k nearest neighbor type. For example, of circle type could be find all points from a location with 1 kilometer radius. So it's given a center location and a radius of 1 kilometer. We want to find out how many points are coming within that. And we also increase the distance to, let's say, 10 kilometers. Similarly, bounding box could be our rectangular based query, which means given a 1 kilometer by 1 kilometer region, we want to find out how many points are within that region. The KNN queries are like finding, give me the k nearest points with reference to a location, like which are the nearest 5 petrol pumps or 10 petrol pumps nearby. Now these kind of queries type represent the common location based queries that we are used to, hence we consider this in this kind of study. So here I'm showing the result of the 7 node comparison with 1 million, 10 million, 100 million and 200 million points, and you can see the latency or the response times, and we can see that among all the queries Presto has performed better compared to the, and then second is the Spark compared to the Hive based solutions which are having a high latency. Now the advantage of having such SQL and Hadoop based framework is we can use it for powering the dashboard based analytics by taking the data sets stored onto those HDFS based system and then powering this dashboard where a decision maker can interact with this, and the backend the queries could be run, and the data that is fetched can be in the real time being analyzed using the point and a click method. Here it is being shown how to analyze the crime data. Now one more study that I wish to share is like analysis of the social media data, taking tourism as the use case. So in this study, the idea was to come up with the framework wherein the social media platforms, multiple like Twitter, TripAdvisor and Flickr, could be used for analysis of the tourism, making sense of the public opinions and identifying the tourism seasonal trend, the sentiment what the user is communicating, which places he is rating them more higher or less. So such kind of studies are useful because compared to a traditional survey based methods, these serve to assist in identifying what are the issues people are complaining, what are the important ratings they are giving to places, and how best to serve them in the near future. Because these platforms support geocoding information, so we could use it to find out, suppose in this case is identifying which type of tourist type they are referring, whether it is a urban, religious and so on, talking about the sentiment they are sharing, whether they are talking about positive sense or negative sense. We could also see how the tourism trends is being changed based on the number of, let's say, the posts being done over the different seasons like winter, summer and so on. And we could also see which are the most popular places based on again the information that people are sharing on those platforms. And then it also helps in maybe identifying, if I could just scroll further to which places the people are rating them higher, which is the top destinations based on the number of posts that we have captured. And similarly, we could also use word cloud to find out what kind of popular hashtags people are using, what kind of negative experience they are sharing, and what are the positive experience they are sharing. So such kind of information becomes quite useful when we want to analyze the trend based on the social media platforms. Now, one more thing that we should also keep in mind is when talking about big data is that to handle such vast and diverse amount of data, we will also require a kind of computing facility or infrastructure facilities. So cloud computing provides the underlying engine over which these kind of distributed processing can happen. Now cloud computing primarily we could define it in the form of an on-demand uh, access to a shared pool of resources. That resources could be network, could be servers, could be applications or services. The advantage is that could be provisions as and when we need it, and could be released when we don't want to use it. So think in terms of like pay per use or a meter service, that just like we use electricity or water in our houses, like on demand access we can use it, and once the demand goes up we could again release back the resources. Now there are primarily three service models when we talk about cloud computing. One is a IaaS, which stands for infrastructure as a service. So AAS will stand for as a service, which means here is infrastructure as a service. PaaS will mean platform as a service, and SaaS will mean software as a service. Now, when we talk about infrastructure as a service, we are primarily talking about using the network-based resources that could be servers, storage locations being handled by the cloud provider. When we talk about from the platform perspective, think in terms of you are given a kind of a notebook based environment to work on with all the Python ecosystem installed, so you can directly build application of top of it. You don't need to configure the machine, install the OS, maintain the versions. Just think in terms of you are given a notebook environment where everything is configured and you can start building your application. Compared to infrastructure as a service where you can rent, let's say, a server resource like in the form of a virtual machine, and then you can configure, install the operating system, the libraries, and before making it ready. Now software as a service is a pure subscription model. Think in terms of an email based subscription service that you can get like a Gmail, where we don't need to maintain the infrastructure, don't need to maintain the platform. You go and access it. You just required internet connections and access to a web browser through which you could access and use that applications. So this infographic primarily talks about what kind of these three platform and what you are managing and what is taken care by the vendor. Now if you compare these three platform with on-premise thing, as you will see that in the on-premise, the complete hardware, the platform or runtime operating system along with the software and other things has to be managed by the individual, whereas in the infrastructure the user only needs to maintain the runtime operating system and the application he wants to build, whereas the vendor takes care of the complete network and storage perspective. In the platform, as you can see from this infographic, compared to the infrastructure as a service, here the vendor takes care of the underlying hardware along with providing the necessary platform or runtime environment, and the user can concentrate more on the actual task, which is in this case is building of the software or application utilizing his own data sets. And compared to the software as a service where the whole stack of storage, runtime, the software is being maintained by them, and then we pay only for the amount of time we are using such systems. Now from the big data perspectives, these kinds of solutions are finding highly usable. Good example is the let's say the geospatial cloud-based platforms. A good example is a Google Earth Engine, which provides a platform for performing this scientific analysis, wherein it provides the geospatial data sets by providing satellite imageries, along with the computing capabilities, along with the application programming interface that you can connect with any desktop software like QGIS also, and you can analyze the data using the cloud-based environment. Now the good thing is the data sets that you want to use are already available. The algorithms are also available, and the code editor along with the code snippets are also made available, and people have found usage in various kinds of domain. That could be forestry, agriculture, health sector, climate change, land use and land cover kinds of processes. So think in terms of cloud-based platform where the data sets, the algorithms are already built in. Now compare this to your traditional based workflow, where first you go to let's say the uh, remote sensing provider website, download the data, do the pre-processing, and then carry on with the workflow in a GIS environment, compared to the data is already available, ingested into the system. The algorithm runs where the data is, and you can run the script using the power of the infrastructure and compute and perform such kind of applications that I'm showing on the left hand side. Now finally, let's also talk about what are the challenges that we could think of. So challenges, as I said, are with reference to the computing infrastructure, because to process such data sets we required such kind of performance systems, wherein we could store such data sets in a distributed environment. And as I mentioned, cloud computing do provide a solution wherein people could utilize it. However, there are other challenges with reference to the security and safety of the data, because people are reluctant to share their data over the cloud. Another challenge is with reference to the data collaboration, which talks about that the data sets that we are interested in are primarily fragmented among the various agencies and partners, and accessing of the data is also a major roadblock. So however, with the coming of open data policies and sharing mechanisms, such problems could be now eliminated. The other thing is we should also care about is called as a big data methodology, because we do know that even though we may be using the distributed environment, but most of the, let's say, the algorithms could not be parallelized. For example, not all existing algorithms can be processed using the distributed manner. So we also have to look from that perspective. And finally, from the pure visualization and interpretation perspective is a mechanism for accessing and visualization of such data sets so that the user can carry out his analysis in easy way. Hence, I talked about examples like dashboard or online processing. These kinds of tools are easy user, so that accessibility could be increased. More users could be readily use it. The decision makers can directly use them without any knowledge of, let's say, GIS working on software per se. So because these kind of dashboard or interactive interfaces provide intuitive environment through which they could play around with the data, analyze based on different scenarios and get the results. So in this topic I talked about big data. So being an overview topic, idea was to give you the various things that we should consider working in such an area of big data analytics. So we define what we mean by big data. So remember that size is only one perspective. Remember the other V's that we talked about, like volume, velocity, variety, veracity, and the value. We also talked about how the big data refers to related to our geospatial, because it fulfills those V's dimension or characteristic that we mentioned. And we also seen the various data sources to the geospatial data sets, followed by the various kinds of analytical frameworks that are available. So we talked about Hadoop-based systems, Spark, and also the how does a cloud computing environments support this geospatial big data, and finally we talk about the challenges. So at this stage I will stop.